Hello and welcome. I am Pedro Lobler, a PhD student at the Power Electronics and Control Group, GEPOC, at the Federal University of Santa Maria in Brazil. GEPOC is a national reference center for research in power converters, control system, and advanced energy solutions. Founded in 1987, the group currently brings together over 30 PhD researchers and more than 140 students across undergraduate and graduate programs. With state-of-the-art laboratory infrastructure and strong partnerships with industry, GEPOC plays a leading role in both academic excellence and applied technological innovation in the field of the power electronics. In this video, I will present the paper entitled A Two-Stage Isolated DC-DC Architecture for EV Auxiliary Power Module. Let us start with the context. In EVs, we have two words, a high voltage domain, 400 volts, sometimes more, and a low voltage domain, 12 volts, where all the onboard electronics live. Breeding these domains is the job of the auxiliary power module. Now, here's the challenge. If you're trying to deliver just a few kilowatts at 12 voltage, that instantly means hundreds of amperes flowing on the low voltage side, and that is where the real challenge begins. That is a lot of current, and it brings serious conduction losses, thermal stress, and overall design complexity. So we asked, how can we make this conversion more efficient, more elegant, and still safe? Our answer is this architecture you see here, a two-stage isolated converter made of a partial power converter followed by a half-bridge converter with a current doubler rectifier. Let me break it down. The PPC, acting as a pre-regulator, takes the wide high voltage input and stabilizes it to an intermediate level, say 250 voltage. But here's the trick. It only processes part of the power, that means less stress, smaller switches, and fewer losses. Then comes the second stage, the half-bridge with current doubler. It runs with a fixed dead cycle of 50%. Why? Because operating at that point enables full ZVS on both sides. Since the input voltage to the half-bridge is lower, thanks to the pre-regulator, we are able to use a low voltage rated MOSFET, which typically have a much lower RDS on. That means less heat, higher efficiency, and cleaner switch behavior, exactly what you want when working with high currents at low voltage. Based on the analytical loss analysis, we can predict that the converter with the pre-regulator state achieves higher efficiency compared to the single-stage solution. Thank you for watching, and a special thanks to the Federal University of Santa Maria, IEEE Industrial Electronics Society for supporting this presentation through the EIS SYPA Award.